Assalamualaikum to my dearest lecturer, Dr. Muhammad Falalu. I'm Sofia Jessica and my partner, Nurul Akila Nabila, will be presenting on laser-induced breakdown spectroscopy (LIBS). Laser-induced breakdown spectroscopy or LIBS is an analytical technique that uses a high-energy laser pulse to analyze the elemental composition of a material. It is functional for a few things, which are firstly, it being used to analyze the element composition of material, which is by analyzing the characteristic light emitted by the plasma. Also, it is a multi-element detection which can detect multiple elements including the light elements, and mostly LIBS have been employed to identify the overall levels of heavy metals in several reference oil samples. LIBS is a real-time analysis since it is also providing rapid measurement of materials. LIBS can be used as a possible online detection technique because of its rapid reaction, multi-element analysis, and convenience to use without sample preparations. And last one, it can be used as a qualitative and quantitative analysis, which is LIBS determine the type of elements and their concentration. Application and characteristic. LIBS mostly being applied in industrial, environmental monitoring, also in forensic. The characteristic of non-destructive testing, portable and flexible to be used on laboratory and field use, and wide applicability, which can be worked with solids, liquid, and gas. All of it makes LIBS a strong instrument to be used for industrial and scientific application. Methodology of LIBS analysis can follow these 8 steps, which are experimental setup, sample preparations, experimental procedure, spectral analysis, error analysis and uncertainty, safety measures, software and computational tools, and limitation and assumptions. Next, I will explain about experimental setup. For laser source and sample position, Q-switch neodymium doped yttrium aluminum garnet laser at 266 nm wavelength has been used and focused on the sample through a lens to form a plasma in ambient air. Meanwhile, for spectrometer and detector, a signal from a laser-induced plasma was collected by an optic fiber and was sent to a spectrometer for analysis. Second step is sample preparations. Material. The sample being analyzed, the type and properties of it, either a solid, liquid, or powder. Next, calibration standard. The samples in LIBS were used for calibration and validation, which means the sample were set to use to build the calibration mode or used to verify the predictive performance of the model. Analysis of LIBS main metrics of performance depends on few factors, which are first, accuracy, and LIBS. The calibration procedure and the quality of the reference data determine accuracy. Factors can affect the accuracy of LIBS such as metric effect, where R is influence intensity, also thermal properties, preparation of surface, and texture of sample. All the factors will affect interaction between laser beam and sample surface, especially the LIBS performance in the analysis. Next, sensitivity. The target element emission intensity and the detector's efficiency determine the LIBS sensitivity. In LIBS, quantification typically represented by the slope of the calibration curve, detection limit or limit of detection or LOD. In LIBS, LOD determined by baseline noise and signal strength of the light. Also for robustness, in LIBS is impacted by modification to the surrounding factors, specific parameters, or sample composition. Lastly, selectivity. It is depend on the ability to resolve overlapping emission lines and spectral resolution and be affected by complex matrices and spectral interference. Data obtained from the analysis with LIBS, which is according to CHM. Based on the data obtained, the emission lines or peak areas for the compounds decrease with the increasing water content. The water in the sample will be vaporized using some of the laser's energy, which would lower the plasma emissions. Matrix effect, which is a water content, is one of the factors can affect the performance of LIBS. However, it can be minimized by using internal standardizations methods.
Despite its many strengths, LIBS does have certain limitations that must be considered. One of the primary challenges is metric effects, where variation in physical or chemical composition of the sample can influence plasma formation and spectral emission. This can lead to inaccurate measurement if it's not properly corrected. Additionally, LIBS may exhibit lower sensitivity for trace level detection compared to more advanced techniques such as induced coupled plasma spectrometry (ICPS), which can detect elements at part per trillion ppt levels. Another issue is spectral overlap, where emission lines from different elements can interfere with each other, complicating the identification process. Furthermore, the initial cost of LIBS system, including high-power laser and spectrometers, can be significant, potentially limiting accessibility for smaller laboratories or institutions. However, the advantage of LIBS often outweigh this limitation. One of the most notable benefits is minimal sample preparation, as LIBS can analyze samples in their native state without requiring complete digestion or treatment procedures. This reduces the risk of contamination and speed up the analytical process. Real-time analysis allow for immediate results, making LIBS ideal for on-site environmental monitoring and quality control. Additionally, LIBS is a non-destructive, preserving the integrity of a valuable or limited sample. Its portability and ability to operate in remote or hazardous environments further enhance its appeal, particularly for field application in geology, mining, and environmental science. To address the limitation of LIBS, several strategies can be employed to improve performance and accuracy. One effective approach is metric matching, where reference materials with similar composition to unknown sample are used to construct calibration curves. This helps minimize metric effects and ensure more accurate quantitative results. Advanced calibration techniques, including the use of machine learning and multivariate analysis, can further enhance the precision and reliability of LIBS measurement. Double pulse LIBS, which involve firing two consecutive laser pulses at a sample, has been shown to significantly increase the sensitivity and reduce the detection limit. This technique enhances plasma formation and prolonged emission, resulting in stronger and more distinct spectral signal. Additionally, conducting LIBS analysis in an argon or inert gas atmosphere reduces metric effects and improves signal quality by preventing oxidation and minimizing interference from air molecules. Therefore, in conclusion, LIBS has proven to be a highly effective technique for the detection and quantification of heavy metals in a wide range of samples. The spectral data obtained in the articles highlight the robust capabilities of LIBS for heavy metal detection and quantification. By leveraging qualitative identification through peak matching and quantitative analysis via calibration curve, the technique provides a comprehensive insight into elemental composition of sample. While the data demonstrates strong performance addressing potential or limitations such as spectral overlap or metric effects through calibration and advanced technique can be further enhanced to reliability of LIBS as an analytical tools.
In addition,
the method's ability to deliver rapid, non-destructive, and real-time results make it an attractive alternative to traditional techniques such as ICP-MS and AAS. Although ICP-MS provides superior sensitivity for trace element detection, LIBS excel in portability, speed, and ease of use, and making it indispensable for field application. The selection of LIBS for heavy metal analysis is justified by its unique combination of accuracy, versatility, and practically reinforcing its importance in modern analytical science.
These are all the references that we had used in our assignment. That's all from us. Thank you.